Let's see this case. In the arrangement shown in the figure, the mass of rod M exceeds the mass m of the ball. The ball has an opening permitting it to slide along the thread with some friction. The mass of the pulley and the friction in its axle are negligible. At the initial moment, the ball was located at the opposite lower end of the rod. When set free, both the bodies move with constant accelerations. Find the friction between the ball and the thread. If t seconds after the motion the ball got to the opposite upper end of the rod, take rod's length as L. So what happened over here was you left the system over here where this was a bead, and the bead slided on the thread with some sort of friction. So if you see just the bead, I'll just draw this as the thread, and on this thread there is a bead of mass m. This goes down with mg downward. Friction Fr tries to oppose it so that it goes down with an acceleration a1, so that on this bead mg minus Fr is equal to ma1. This becomes my equation number 1. Or a1 over here becomes g minus Fr by small m. Similarly, let's see how friction affects tension. Now if you see the string and the bead, see over here friction was applied by string on bead. So every action has its equal and opposite reaction. So the bead would apply friction on the string. And if you cut a section of the string over here is massless. So that if you see it with the other section would be applying a tension T on the string. Where a massless thing has net force equal to mass into acceleration. But since it is massless, so net force has to be 0. So tension T developed in the system must be equal to friction. Now see this block over here. This body at the top experiences tension T. In the bottom direction experiences gravity mg, and it goes down with an acceleration a2. And mg minus t can be written as capital M into a2, where t was equal to Fr. So mg minus Fr can be written as capital M into a2. So acceleration a2 over here can be written as g minus Fr by m. Now start seeing them separate together. See, this was the bead over here, and this was the rod over here. Rod was going down with a2, bead was going down with a1, so that this length was L, and they said that this started at t is equal to 0, such that at time t is equal to t, what they saw was that both of them went down and the bead came at the top end of it, somewhat like this. The situation was somewhat like this at time t is equal to t. Now if this has traveled x1 and this has traveled x2, then clearly from here x2 minus x1 would be the length of rod. x2 can be written as half acceleration of 2 into t square, whereas x1 can be written as half acceleration of 1 into t square, can be written as L. So a2 minus a1 can be written as 2L by t square. a2 is g minus Fr by capital M. a1 was g minus Fr by small m, was 2L by t square. A g and a g over here gets cancelled. So Fr by small m minus Fr by capital M is 2L by t square. So Fr times capital M minus small m upon capital M into small m is 2L by t square. So the value of friction over here is 2 capital M small m L by capital M minus small m into t square. That's the answer required.